In this section, we're going to keep working on different integration techniques and different types of expressions that we can integrate. Particularly, we'll be looking at functions that involve trig integrals. Now, there's a couple of trigonometric identities we'll want to be able to work with. Our Pythagorean identity, sine squared plus cosine squared equals 1. Notice that I always put parentheses around the arguments of my trig functions, and I think that that's an important thing that you should be doing as well. Sometimes the trig functions aren't always going to be just an x, and it's important that we be able to see what exactly the trig function is. Another trigonometric identity, 1 plus tangent squared equals secant squared, and 1 plus cotangent squared equals cosecant squared. And of course, these other two can be derived from the first pretty easily if you'd forget. We also have our half angle identity, sine squared of x equals 1 minus the cosine of 2x all over 2. And then cosine squared also has a similar one, except it's a positive 1 plus cosine of 2x all over 2. These are called half angle identities because if you notice over here where we have the 2x, we split that in half when we go back to the x, so it's half angle identity. And then we have a couple double angle identities as well. Now there's many more trig identities than these. These are just a couple that will show up pretty commonly, so they're good ones to be aware of. Sine of 2x is equal to 2 sine x cosine of x, and the last one that I'll list here, cosine of 2x is equal to cosine squared of x minus sine squared of x. And again, there's many others. These are just a few that are nice to work with. Now, some of these trig integrals, we don't really need any other rules other than a nice straightforward use substitution to work with, but other ones will need a few different rewrite techniques in order to work with. Let's go ahead and look at a first one. Let's look at sine cubed of 2x, cosine of 2x dx. Now what we want to think about here are derivatives and antiderivatives. So if we look at this particular function in terms of derivatives, I know the derivative of sine is cosine, so it looks like when I set this one up, I can just use u to equal the sine of 2x. du then would be the derivative of sine of 2x is equal to 2 cosine 2x dx. So I have my u and I have my du. It looks like the only thing I need to miss, the only thing I am missing is a 2, so I'll compensate by multiplying by a 2 on the inside and a 1/2 on the outside. So rewriting, I have 1/2 the integral. Sine of 2x was u, so this is going to be u cubed, and then 2 cosine 2x dx is my du. So this is just a nice little u substitution. When I integrate this, I'll add 1, divide by the sum. So I'll have u to the 4th over 4. So this is 1/8 u to the 4th, and we know u though is sine of 2x, so this would be the sine to the 4th of 2x plus c. So there's my integral, and again we can check our solution by taking the derivative, and you're welcome to go ahead and double check those. So this one, no special rules, just a nice little straightforward u sub. So all of these problems that we're working with, the first thing I would do is check to see if our old techniques, a u sub, would work. If that won't work, then we're going to have to try and come up with something else. So again, we want to be thinking about u's and du's. Let's think about that sine cube that we were just working with, and what would we do if there was no cosine to go with it? Well, we can't use our u sub here because you can see from up here my u would be sine, but my du would be a 2 cosine, and I don't have that. But I think we could get a cosine involved in this if we think about our Pythagorean identities. So let's go ahead and rewrite this as sine squared of 4x times the sine of 4x. And again, sine squared times sine is sine cubed. And then what I'll do is I'll apply my Pythagorean identity to this piece right here. Sine squared plus cosine squared is 1. So sine squared would equal to 1 minus cosine squared, and of course the argument is 4x for this particular case. So I go ahead and rewrite 1 minus cosine squared of 4x dx, or sorry, not the dx yet, then I have my sine of 4x dx. So it looks like to me I split this out. I saved a sine for my du, and I'm going to convert the rest to cosine by applying my Pythagorean identity, and now I'll expand. And what we mean by expanding is by distributing. So rewriting here, the sine of 4x times 1 is just the sine of 4x, and then minus, I'm going to split this up into two integrals, cosine squared of 4x sine of x dx. sine of 4x dx. So now I have two different integrals to look at. I'm going to rewrite these again down here. I kind of ran out of room on the end there. Now each of these will require a different integration technique to complete. So you have to make sure that you show that work. And in this particular case, u would just be 4x, du would be a 4 dx. So I'd multiply by a 4 on the inside, compensate with a 1/4 on the outside, and I'd have 1/4 integral, and this would be the sine of u du. And I'm just going to go ahead and keep working on this one integral until I get it finished. The integral of sine is a negative cosine, so this would be a negative 1/4 cosine of u. But we know u in this case was 4x. So this is one part of my solution. And a lot of times these problems get so involved that I have lots of different pieces and parts running around, so it's a good idea to make sure that you mark every solution and then remember to gather them again at the end. Here we're going to use a nice little straightforward u substitution. U is equal to the cosine of 4x. Du is negative 4 sine of 4x dx. So the derivative of the cosine of u is the sine of u prime. And then I make that substitution. I'm missing the negative 4, so I guess I have this negative on the outside, but I'll just leave it there. And I'll multiply by negative 1/4 on the outside. A negative times a negative is a positive 1/4. And then this would be cosine squared, so that would be u squared, and then all the rest would be make up my du. So this is 1/4 u cubed over 3. But I know what u is. U was cosine, so this would be cosine cubed of 4x. So I have these two pieces here. So rewriting our solution, I'd have a negative 1/4 cosine of 4x plus 1/12 cosine cubed of 4x as my solution, and of course my constant of integration. So this is my solution. It's not the only solution, and it's not really our simplified solution, so I'd like to take this a step further. To simplify, we would find a common denominator and we'd factor. Now one of the reasons we'll want to do this is evaluating these, because not all of them will be indefinite integrals, and another thing that we'll be looking at eventually is not only evaluating these but possibly applying L'Hopital's rule to these, and of course with L'Hopital's we need a fraction, a numerator, and a denominator. So being able to simplify is a good thing to go ahead and get started with here. Negative 1/4 would be the same as negative 3/12 as our common denominator. And then as soon as I have that, I can see that I have a 12th out front. And I also have a cosine of 4x. And we usually like our coefficient, our leading coefficient, to be positive. So I'm going to go ahead and write this piece first. So that would be cosine squared of 4x minus 3. And then of course they're my constant of integration. So simplify completely. So what we did is we found a common denominator, and then once I found that common denominator, I factored it completely as well. So a simplified solution would be here. So in this particular case, we had to create our own du by rewriting our trigonometric integral, our trig integral, to a form where I could apply some Pythagorean identities. Now there are a set of rules that we can follow for some of these, and I'll summarize those at the end, but I kind of want to just kind of look at these each one at a time and see if we can logic our way through toward a solution, because on a test sometimes you might not have access to all of your formulas if you didn't put it on your note card, so it's good to have some strategies outside of that. Okay, let's look at another one. Now the one we just looked at, the sine cubed, we could use that exact same strategy with cosine cubed. I could save out a cosine and then convert the rest to sine and expand and integrate. So that idea of splitting apart and converting is going to be a very important idea. On our next one that we'll look at, let's look at an even power. Let's look at the cosine to the 4th power of 3x dx. Now for this one, if I saved out a cosine, then I would have a cosine cubed, and I don't have an identity for cosine cubed. So that strategy that we used before isn't going to really work now. So I think what I'll want to do here is I want to apply a rewrite and then my half angle identity that tells me that the cosine squared, if we go ahead and scroll up here, the cosine squared of x is equal to 1 plus cosine of 2x over 2. So cosine squared of x is equal to 1 plus the cosine of 2x over 2. Now what we have here is, though, we have the cosine squared of 3x. So that's 1 plus the cosine. So I need to double it. So this was a 3x. If I double it, it becomes a 6x over 2. So that's the rewrite that I'm going to use. Now recall that cosine to the fourth, of course, would be cosine squared times cosine squared. So when I rewrite this, it would be 1 plus the cosine of 6x over 2 times 1 plus the cosine of 6x over 2 dx. So I can pull this coefficient out. 2 times 2 is 4, so I have a fourth out front integral, and then I FOIL this out. So my firsts, my outsides and insides combine, and then my lasts. Now there's several different ways we could work this problem from here. I could integrate each piece separately, or I know I'm going to have to make a substitution here for the cosine squared to integrate it. So I think for this piece right here, I could think about rewriting this cosine squared. So let's go ahead and, actually I think I'll split this out into 3 different integrals just so it doesn't get confusing. Things to remember, there's a fourth out front of each one. So I'm going to pull the 2 out with it as well. 2/4 cosine of 6x plus 1/4 cosine squared of 6x dx. So we have some easy parts here. The integral of 1 dx is x. So this piece right here would be 1/4 x. This next piece is going to be, I have the 2/4 is the same as 1/2, but I'll also have a 1/6 out front, and the integral of cosine, of course, is sine of 6x. And I'll show my work to support that in a moment. And then this next one, I'm going to have to totally rewrite that. Cosine squared of 6x, that's going to be 1 plus the cosine, I have to double this from 6x to 12x, all over 2 dx. Okay, that comes right up here from this identity that we're using. So we take our argument that we have here, and then we have to remember that this is actually half of the angle that I come up with over here, so I need to double it to move across. Now I need to show a little work here to support this one. So for here, we let u equal 6x. du would be 6 dx. And so what I have here then is I have a 1/6 on the outside, compensate with the 6 on the inside. I drop my dx here, which I should not have done. And so when I integrate this, I'm going to end up with the integral of 1/6 cosine of u du, which of course is 1/6 sine of u, and u is equal to 6x. And so that's where this came from. So there's my supporting work. Now over here, there's the half out front came from right here, if you're stuck there. So including that, that would leave us with 1/12 sine of 6x. So if I'm keeping track, these are my first two. Now there's quite a bit of work here involved in this next one. I'm going to split this up into 2 integrals again. 1/2 plus cosine of 12x over 2 would be one way I could split this up. Another thing I could do is I could just go ahead and pull this 1/2 out front right away and then split this up into 2 integrals. And I think that's easier to get rid of that fraction. So this would be 1/8 the integral of 1 dx plus 1/8 integral cosine of 12x dx. Okay, so this is an easy one. The integral of 1 dx is just x, so this piece is 1/8 x. So there's a part of my solution. And then over here, I would let u equal 12x. du is 12 dx, so I'd multiply by 12 on the inside, compensate with the 1/12 on the outside, and it looks like I have 1 over 96 integral cosine of u du, which of course we know from before the integral of cosine is sine of u, but u is different this time, it's 12x, so make sure we have that update. And so this is the fourth part of my solution. So we have to combine all these. So here I'd have a fourth x plus a 12th sine 6x plus an 8th x plus a 196th sine 12x. Looks like there's some like terms I can combine here. So a fourth would be the same as 2/8 x, and of course that would combine here with that 1/8 x to give me my 3/8 x, plus 1/12. Now one caution I'll give you is when you check your answers on Mathway or Wolfram Alpha or something like that, they apply some very, very funky trigonometric identities sometimes. So you might do your handwork and get this nice little solution, and their answer might not look anything like it. So it doesn't mean you're wrong though, it just means that they've applied some trigonometric identities. So the best way to work with that is you would take your answer and subtract it from their answer, and if you get 0, they are equivalent expressions. Okay, so good way to check this is to take your answer minus Wolfram's answer, and if you get 0, then they're equivalent solutions. Now here we'd find a common denominator, so we'd multiply top and bottom by 12. Here we'd multiply top and bottom by 8. So I'd have 36x plus 8 sine of 6x plus sine of 12x all over 96. Now there's really nothing I can factor out here that's common. I could rewrite these into other trig identities and try and do something there, but I think that this is about as far as we can take this solution. If you want to pull the 1 over 96 out front, you could, but this is actually in perfect spot here to go ahead and evaluate an expression or take a limit if we needed to at some point. So simplifying these are going to be a big deal because when you're simplifying, there's some trig identities that you can apply, and the list I gave you up front is a good list to keep in your notes, but it's not necessarily an exhaustive list, meaning there's others that we could kind of pull out of our pockets if we needed to as well. Let's go ahead and look at sine cubed of 4x, cosine to the negative 2 of 4x dx. Now if we wanted to, we could flip this cosine underneath into the denominator because of the negative 2, but that's really not going to help us integrate this. So I think what we want to do is the derivative of cosine is sine. It's negative sine, but we can compensate for the negative. So if I could save out one of these signs and then convert the rest, I think I would be good. So some of these strategies, what we're going to start doing is I'm going to help you start setting these up, and I'll leave the integration parts to you as soon as we get the setup done, because I want to make sure we can work through a lot of these to get set up. So sine squared is equal to 1 minus cosine squared of 4x, applying the Pythagorean identity. So it looks like we have 1 minus cosine squared of x, 4x, cosine to the negative 2 of 4x, and then I have my sine of 4x dx out back. Now the reason I put this on the end is this will eventually be my du. So we saved out a sine, we converted the rest to cosine, and now we're going to expand and integrate. So I'll take this and distribute, and I'm going to distribute not only the cosine but also the sine. So as I distribute, this would be cosine to the negative 2 of 4x sine of 4x dx. I'm going to split this up into pieces as I go. Cosine squared of 4x cosine to the negative 2 of 4x sine of 4x dx. Now this first one, it's ready to go. This one we can simplify a little bit more. Now if you think about this, we're multiplying like bases, and when we multiply like bases we add exponents. So this would be cosine to the 0 of 4x, and anything to the 0 power is 1. So this whole piece goes to 1, and I'm just left with 1 times the sine of 4x. Now down here we will have u equal cosine of 4x. du would be negative 4 sine of 4x dx. So the idea of that substitution is going to be important. I need to compensate for this missing negative 4. So this would be u to the negative 2, and then this negative 4 sine 4x dx is du. Add 1, divide by the sum, and I end up with 1 over 4u. for this first one. And of course we know u is equal to 1 over cosine of 4x. Now I could rewrite that 1 over cosine. Of course we know that 1 over cosine is going to be secant, so we could work with that as well. But I'm just going to leave it right now in terms of cosine because I want to see what my other term will look like first. So for this other one, I just have minus integral sine of 4x dx. U is 4x. Du then would be a 4 dx. So I multiply by a 4 on the inside because I'm missing this 4. Compensate with the 1/4 on the outside. I'll put it in down here. So I have minus 1/4 integral sine of u du. Now the integral of sine is a negative cosine of u. U in this case is 4x. So for this piece I'm left with 1/4 cosine. So cosine of 4x over 4. So when I rewrite these and I'm adding them together, I have 1 over the cosine of 4x. I think there's a 4 here that I'm missing. Yeah, this 4 right here needs to be here. Okay, plus cosine of 4x over 4. Now this is a solution if I include the plus c here, but it's not my simplified solution, so there's a couple different things I could do here. I see that there's a 4 that's common, and I see I could flip this up top. So whenever I can, I want to be able to rewrite these as a single fraction with a common denominator. If I wanted to multiply top and bottom by cosine, I could do that as well. But I think I already have this as a nice rewrite. 1 over cosine is secant. So this would look like secant of 4x over 4 plus the cosine of 4x over 4. And of course now I can rewrite that as a single fraction with a common denominator. Again, many other ways we could simplify this as well, but what we're shooting for in simplification is a common denominator and a factored expression, so we have a single fraction when we get done. So this is just another example of that idea of saving out a sine, converting the rest to cosine, expanding and integrating. And that's going to be a big idea. Whether we save it out as a sine or cosine, tangent, secant squared, it will depend on the problem, but that concept will be showing up a lot. Okay, we've been working a lot with sines and cosines. Let's go ahead and look at some other trig functions. Now we do have some strategies to work with other types of trig functions in terms of like saving out part of the trig function. But one of the things that I always think about when I'm working with non-sines and cosines in an integral is I think about rewriting in terms of sines and cosines. So if I don't see anything that's going to work off the bat right away, like some sort of a u du, which I don't see happening here, I'm going to rewrite this in terms of sine and cosine. Now the reason this sometimes works is I can recognize my derivatives and antiderivatives a lot easier. So a couple things I know. Cosecant is equal to 1 over sine. So this would be 1 over sine to the 4th of x. And then I also know that cotangent squared is cosine squared over sine squared of x. And of course when you divide by a fraction you're multiplying by that reciprocal, so I'll multiply by the reciprocal of the denominator, so the sine squared will flip up top. And then I have some simplification that can occur, so this sine squared cancels down here to leave me with a sine squared in the denominator. And then rewriting this, it looks like I have 1 over sine squared cosine squared. Now there's several different ways that we can go from here, but one thing I would like to do is I'd like some of these sine squareds and cosine squareds to cancel, because if they would cancel I would have some nice little antiderivatives to work with. So, and this is just a trick that I've learned, and so I'm going to pass it on to you. This value of 1 here, I know that sine squared plus cosine squared is equal to 1. So I'm going to take that and substitute in. So my numerator will now become sine squared plus cosine squared. And again, I'm just applying that identity. Now my strategy from here would be to go ahead, these are multiplied not added, would be to go ahead and separate the numerator. So I'd end up with sine squared, cosine squared in my denominator, and sine squared would be in my numerator. So that would be one of my fractions. I'll put a dx in here. I'm going to split these apart. And my other one would be sine squared, cosine squared, and dx. Cosine squared x in my numerator. Now simplification can occur here. The sine squareds cancel, leaving me with 1 over cosine squared. The cosine squareds cancel, leaving me with 1 over sine squared. So rewriting, I have 1 over cosine squared plus 1 over sine squared. Now it doesn't look like anything real obvious here until I rewrite these. 1 over cosine squared is secant squared, and 1 over sine squared is cosecant squared. Now again, I always say think about derivatives and antiderivatives. So the thing we want to think about here is the derivative of tangent is secant squared. Therefore the integral of secant squared is tangent. Antiderivative here. Same thing over here. The derivative of cotangent is negative cosecant squared. Therefore the integral of cosecant squared, I just move the negative across, is negative cotangent. So I'm using that idea of an antiderivative. So this would end up looking like tangent of x. So for this first one, the integral of secant squared is going to be tangent of x. So this is tangent of x minus cotangent of x. And of course this is a nice little expression. I need my constant of integration, and this would be nicely simplified. However, we usually like to have a common denominator, and we also like to have these in fraction forms sometimes. In this one it's not really necessary, but if we were to evaluate this and we wanted to look at this in terms of L'Hopital's, you'd need a numerator and a denominator. So I could rewrite this. I'm not saying it's necessary on this one, I'm just saying sometimes you might have to. So we would go through and we'd rewrite back in terms of sine and cosine. Find that common denominator, multiply top and bottom by cosine here, multiply top and bottom by sine here. So this would be equal to sine squared of x minus cosine squared of x all over sine x cosine x. And if you recall, if you want to scroll up and have a look, we know that sine squared minus cosine squared is equal to the cosine of 2x. Okay, so a rewrite here would be cosine of 2x all over sine x cosine of x. Now this is a nice little rewrite, however we have a bit of a problem here. This argument is 2x, this argument is x, and I don't like to have mixed arguments if I can help it. I like to have both of them as single x's or both of them as 2x's. So what I'm going to do is I'm going to multiply top and bottom by 2, and then I can apply another trigonometric identity. 2 sine x cosine x is equal to the sine of 2x. So I'd end up with 2 cosine of 2x in the numerator and over the sine of 2x in the denominator. And of course we know cosine over sine is cotangent of 2x plus c. So there'd be another simplification. Just another way to rewrite this. Sometimes they have to be in different forms in order for us to work with these. One thing that I do see here is I think I applied this identity wrong. So let me jump up here real quick. The identity is the cosine of 2x is equal to cosine squared minus sine squared, but let's go up and check. I knew it was close, just not close enough. Yep, cosine squared, I'm looking right here, cosine squared minus sine squared. And I don't think that was in that form. So let's go ahead and rewrite that. Cosine squared minus sine squared. So this is close but not quite. So we'd pull out a negative, and when I pull out a negative, our signs would flip, and this would become a negative as well. So then I end up with my negative 2 cosine 2x. So that works perfect. So be careful when you're using your trig identities, like the mess up I made. I had the order wrong, which usually doesn't matter with multiplication and addition, of course, but it certainly will with subtraction and division. So that one was kind of a long one in terms of simplification, all the different ways we could rewrite it. But I want you to see that sometimes your answer is not going to match Mathway or Wolfram Alpha when you're checking your work. But the handwork that you get doesn't usually match theirs because they apply a lot of interesting trig identities. Let's go ahead and look at a tangent. Let's do tangent to the fourth of x dx. Now I see quite a few ideas that we could do here. We could rewrite this in terms of sine and cosine, and then I could try and use my double angle or half angle identities here. I also know that the derivative of tangent is secant squared, so that's kind of interesting. So here, I think what I'll do is I'll split this out and rewrite it as tangent squared times tangent squared. And then I'll think about 1 plus tangent squared, I know, is equal to secant squared. Okay, so that's interesting. So I'm going to take one of these tangents and I'll rewrite it, one of these tangent squares, and rewrite it as secant squared of x minus 1. Okay, so I'm going to rewrite this. Secant squared of x minus 1. Always put the parentheses around the arguments of your trig functions. It's going to be important when we start evaluating these. And then I have this tangent squared as well that I was just dragging along. So tangent squared of x dx. So I saved out a tangent squared. Okay, and then I converted it to secant squareds. And so now I'll do the expand and integrate bit. I hope this works. So as I expand, I'll have secant squared of x, tangent squared of x dx. I'm going to split this off into two integrals right away. Minus tangent squared of x dx. Now for this first one, this is a nice little u to u. So u in this particular case would be tangent of x. And then du, the derivative of tangent, is secant squared of x dx. So this bit is my du, and this bit would be my u squared. So this is just the integral of u squared du, which is u to the third over 3. U in this case is tangent, so this would be tangent cubed of x over 3. So there's my first bit of my solution. Now what about this tangent squared? I don't know the integral of tangent squared because I don't have an antiderivative here, but I can rewrite this again. So I could look at this as, remember we just rewrote this earlier, secant squared of x minus 1 dx. And I'll split this up into two different integrals. Now be careful with this negative. When I talk about this negative, it distributes here and here, so that's why this became a positive. Now the integral, the antiderivative of secant squared is tangent, and the integral of 1 dx is just x. So here's my other piece to this. So it looks like to me I have tangent cubed of x over 3 minus tangent of x plus x. So there's my solution. We like a common denominator and we write these as a single fraction. So here I'd multiply top and bottom by 3, top and bottom by 3. So this would be tangent cubed of x minus 3 tan of x plus 3x all over 3 plus c, my constant of integration. So rewriting, simplifying means finding a common denominator and rewriting things in terms of a simplified fraction or a factored simplified fraction. So our strategy there was we realized that tangents and secants kind of go together with antiderivatives, and we used our Pythagorean identity to rewrite. Let's go ahead and look at cotangent cubed. Now most of the ones we're looking at today are indefinite integrals, just because if we had definite integrals we would just evaluate these trig functions and it would just take some extra time, and all you really need to do is apply your unit circle there. So in your handwritten homework you'll see lots of definite integrals. Here we're focusing on indefinite so we can look at the integration. Now here we're going to use, there's no u to u type of situation here, so I'm going to use the Pythagorean identity 1 plus cotangent squared of 2x is equal to cosecant squared of 2x. Solving for cotangent squared of 2x, I get cosecant squared of 2x minus 1. Okay, so I would rewrite this as cotangent squared times cotangent dx. I know cotangent squared is going to be equal to my Pythagorean identity. So that's going to be cosecant squared of 2x minus 1. Now remember, the reason I want parentheses around the arguments of your trig function is if you didn't have parentheses, you'd probably write it as 2x minus 1. And then this begs the question, is the argument 2x or is the argument 2x minus 1? So that's why you'll always use your parentheses here around the actual argument to clarify that. Okay, so we saved out a cotangent squared, or a cotangent. We converted the cotangent squared. Now we will do our expand and integrate. So I have cosecant squared of 2x, cotangent of 2x dx, minus the integral of cotangent of 2x dx. So here we have a nice little u substitution. The derivative of cotangent is negative cosecant squared. So u is cotangent 2x. du is negative 2 cosecant squared of 2x dx, which I have. So I have to multiply by negative 2 on the inside, compensate with a negative 1/2 on the outside. And this is just u squared du, which of course integrates into negative 1/2 u cubed over 3. So negative 1/6 u was cotangent, so this is cotangent cubed of 2x. Now this bit over here, I'm going to rewrite cotangent as cosine over sine. Now we haven't seen this one in a while, but this u substitution is going to put me toward a transcendental solution. So u is 2x, sine of 2x, du is 2 cosine of 2x dx. So this is 1 over u du. The only thing I'm missing is a 2 on the inside and a 1/2 on the outside. So this 2 cosine 2x dx becomes my du. Now this integrates into minus 1/2 natural log absolute value of u, which is the sine of 2x, plus c. So that one we haven't really looked at logs in a while, so make sure that you run through that one a couple times. We're going to find that common denominator. There's not really much we can do with this one. So I end up with minus cotangent cubed of 2x minus 3 natural log absolute value of the sine of 2x all over 6 plus c. So we're rewriting this to that common denominator. Now, it looks like to me we need to double check through something here. Where did that 1/6 come in? Okay, I think it's right here. When I rewrote this as cotangent of 2x, I only have cotangent of 2x to the first power, so this isn't squared here. This would just be to the first. And then when I integrated it would be squared over 2. So this would be a fourth. I'm glad I caught this. So this is negative 1/8. And this is just u. And that's going to change my common denominator to multiplying top and bottom by 4. And so when I multiply that top and bottom by 4, my common denominator is an 8. So this would be an 8 over here, and this would be a 4. Sorry about that. And I think my power, when I integrate, would be u squared, because it was a cubed, u squared. There. I think we've got this cleaned up. So rewriting this with the common denominator, negative cotangent squared of 2x minus 4 natural log absolute value of sine of 2x all over 8, and of course plus c, your constant of integration. So we've looked at quite a few different strategies. Let's summarize those all in one spot. Now when I'm working with an integral, I usually don't go after these rules particularly. I usually try and just look at the integral that I'm giving and then try and figure out if one of these general strategies will work. But there are some strategies that consistently work for some integrals. So if I have trig integrals involving sine and cosine, there's a couple of strategies that I can go after. Now these don't always work, but they're kind of a place to start. So if I have a trig integral that has a sign that is odd and positive, and we had one of these as well, my strategy then would be to save a sign and then take the rest and convert to cosine. And then what I would do is expand by distributing and then integrate my solution. So that's my strategy. Now the same exact strategy will work very well if we have a cosine power that's odd and positive. So we'd save out a cosine, convert the rest to sine this time, not cosine, expand and integrate. Okay, the other one that we used is we had both sines and cosines were even powers, and then we applied our half angle identities. And the ones that we looked like, they were even and positive. Now we did have that one with a negative cosine, but it ended up following a different rule. So here we'd make repeated use. Maybe you have to use them more than once. So we make repeated use of our half angle identities. And those half angle identities were sine squared equals 1 minus cosine of 2x over 2, and cosine squared is equal to 1 plus the cosine of 2x over 2. So those were if we have sines and cosines. Now, U substitution is the first thing you should look for in any of these, and sometimes we'll have to do some other rewrites and some other strategies, but these are a good place to start if U sub doesn't work. And then if U sub doesn't work, sometimes we have to rewrite these using some trig identities before we can get them to integrate. So we have some similar rules if we have integrals involving secants and tangents. For our first case, if secant is even and positive, what we can do here then is we can save out a secant squared and convert the rest to tangent using a Pythagorean identity, and then of course expand and integrate. Okay, now what if tangent is odd and positive? So if tangent is odd and positive, what I can do here is I can save a secant tangent. We didn't see one like this. So save out a secant tangent. And U, I should use a U up here. U represents the argument of the function, whatever it is. So save out a secant tangent, convert the rest to secant. And the reason that we'll do this is the derivative of secant is secant tangent. So convert the rest to secants, expand and integrate. So again, if you look at these problems and approach these problems in terms of derivatives and antiderivatives and looking for those patterns, that will be a huge help. Okay, last one, we kind of did this one already. This is when we had a tangent, I think we had a tangent to the fourth if I recall, was even, and in this particular case positive, and there's no secants. What we did is we convert the tangent squareds to secants. So convert one of the tangent squareds to secant squareds using a Pythagorean identity. Then expand and repeat as necessary. And so you may have to repeat the expansion and then of course integrate. Now if none of these work, and there's a pretty high probability that none of these will work, convert everything to sine and cosine and hope that you can find a pattern or find an identity that will help you integrate. So if all else fails, try converting to sines and cosines. Now some of these are kind of tricky in that on an exam, I really wouldn't expect you to spend half an hour finding the combination that works correctly if none of these rules work. On a homework, you might have a little bit more time to do that, or a handwritten homework. So on an exam, I'm not going to expect to throw any tricks at you unless I give you an identity in the problem. For instance, in the problem that we looked at up here, where we rewrote that numerator with a 1. So when we looked at this bit of a trick right here, in the example, if I wanted you to work this on an exam, I would probably say hint sine squared plus cosine squared equals 1. So that would kind of give you a hint to the rewrite here. Okay, so on the exam we'll focus on the rules or straightforward integrations and evaluations. Any of these types of tricks would show up more on a homework assignment. As usual, if you have questions, let me know. I'm happy to help taking a screenshot of your question. You also have the Pearson Connect to a tutor option as well. Again, please feel free to let me know if you have questions. If you want to set up some online office hours, we can do that as well. Good luck, and I hope you enjoy working on these problems since we get to do a little bit of trig.